We have a lot of different type of problems today. So we're gonna cruise pretty quick. We're gonna list all the transformations based off the parent function. Now, the parent function here is like y equals x squared, which, if you remember, anything to the second power is a u-shaped parabola. But like, what do these other numbers tell us? Because that's a lot different than the equation y equals x squared. Well, the negative in front would show it's reflected. The 3, remember, shows like a stretch or compression. So if that number is bigger than 1, it would show a stretch. So we'd say stretch by a factor of 3. Cool, that's all handled. This plus 8, grouped with the x, that's your horizontal translation. So if it says plus 8, that's actually going to shift it left 8. Left 8. And that, like, in the normal formula is called like h. And technically h is negative 8, which would show it's shifting to the left. And then at the back, you have that minus 11, and that would shift it down 11. So this graph, this U-shaped graph, would be reflected. It'd be upside down. It'd be stretched by a factor of 3, so it'd be way skinnier. It would be left 8 units. It would be down 11 units. Cool. Number 2 shows a square root function, which square root graphs look kind of like a half of a sideways parabola. But the 1/4 in front, out in front always shows a stretch or compression. Since this is between 0 and 1, this would show a compression by a factor of 1/4. The only other transformation is this minus 1 here. Again, it's grouped with the x. That shows a horizontal transformation. So it would shift right 1 unit. Right 1. Awesome. That was fun. Real fun. All right, old exponent properties. Now, if you were looking at number 3, what I would do would be combine these two inside the parentheses together. When you multiply with the same base, you just add the exponents. So that would be x to the 10th in there. And now when you go power to a power, that's where you multiply. So that would give us x to the 50th. That's old algebra 1. Same with this. So when you have a fraction, when you're dividing and the base is the same, you just subtract them. However, if you look at 8/6, they don't have the same base, so we can't subtract. But just simplify the fraction to 8/6. They're both even. So if we divide them both by 2, we'd have 4x to the 10th over 3x to the 14th. But the x to the 10th and x to the 14th, they're only going to be in one spot, either on the top or on the bottom. And here's a hint, they're always going to end up where there are more. So are there more in the numerator or denominator? Obviously there are more in the denominator. So that's where they're going to end up. And then you just subtract. 14 minus 10 is 4. So we have 4 over 3x to the 4th. Remember that in Algebra 1? Remember that in pre-algebra even? All right, here we go. You can't leave radicals in the denominator. You know this. We've done this pretty recently. So what you do is you turn it into a perfect square by rationalizing the denominator. If I multiply by root 3 on top and bottom, this becomes 6 root 3 over root 3 times root 3 is root 9, which then you're like, all right, great, the square root of 9 is 3. So we have 6 root 3 over 3. Oh my gosh. My. Ah. And then you would just check if you can simplify outside the radical. 6 divided by 3 is 2. So this would just be 2 root 3. That would be your final answer. Now this one, I made it a doozy on purpose. We're going to simplify this radical with perfect cubes because it's a cube root. So I'm thinking of numbers that I can cube root. One that goes into 54 is 27. So 54 is 27 times 2. So I put all my perfect stuff in the left radical, and I put all my left 27, I can't cube root 2. Now as far as exponents go, if it was a square root, the exponent would have to be a multiple of 2. If it's a cube root, the exponent has to be a multiple of 3. So x to the 13th, that's not perfect. But x to the 12th is, where does that 13th one go? In the leftovers. Y to the 5th, that's not a multiple of 3, but we could put 3 of them there. The other 2 go in the leftovers. And then if you look at z, 300 is a multiple of 3, so we could put all of them there. Great, here we go. So we have 5 times cube root of 27 is 3. And then when we're cube rooting these things with exponents, all we do is divide the exponent by 3. We divide it by whatever number's here. 12 divided by 3 is 4, so x to the 4th. For the y, 3 divided by 3 is 1, so it'd be y to the 1st. And then the z, 300 divided by 3 is 100. And then we can't do anything with this 2xy squared. Last thing left to do, we can still do 5 times 3. It's 15, x to the 4th, y to the 1st, z to the 100th, times, I like putting the multiplication in there, just so I can see it separate. Otherwise it might look like z to the 1003rd power. But that would be our final answer. That was brutal. That was a toughie. But we did it. Wow, we did it, guys. All right, the fraction exponents. 125. The denominator becomes the root we're looking for. So we're looking for the cube root. The numerator can either go in there with the 125, or in almost every case I would recommend just putting it on the outside. So we're going to cube root 125, and then whatever we get, we'll square it. So the cube root of 125 is 5. And then 5 to the 2nd power is 25. So over here, the 2 would go here. You could write it there, but the nice thing about square roots is like it's an invisible 2. So you don't need to write the 2 there. And then the 5 goes on the outside. Now, what is the square root of 9? 3. And then we would just do 3 to the 5th. I don't remember what that is. 243. Sweet. Now we're going to do equations with those type of problems. There it is. So you have to isolate the base with the exponent. So like on number 10 here, I would have to get rid of the 2 first. The way we're going to get rid of the 2 is dividing both sides by 2. So we'll have 4x minus 1 to the 2/3 equals 9. And then to get rid of that exponent of 2/3, we're going to make the reciprocal exponent on both sides. 3 over 2. So this will all cancel out on the left. So it just becomes regular 4x minus 1. But this 9 to the 3/2, we're going to do what we were just doing. But here's the tough part about these. When you're solving equations and you're square rooting a positive number, you have to include the positive and negative version. So when I square root 9, I have to think of that as 3. Or also, it could be negative 3, which will give us different answers in the end. So 4x minus 1 equals positive 3 to the 3rd is 27, or 4x minus 1 equals negative 3 to the 3rd power is negative 27. Woo, trickery! Same 2 steps though. We're going to add 1, so 4x equals 28. We add 1 over here, 4x equals negative 26, and then we'll divide by 4, x equals 7, and if we divide 4 here, we'll just simplify the fraction, negative 13/2. Again, these are like pretty brutal examples of it. The ones that are going to show up on your test are pretty basic by comparison. But we're going to isolate the number with the exponent. So here, I could add 10 to both sides, so we'd have 3 times 25x to the 2/3. If I add 10 to 65, I'm at 75. Then we would divide by the 3 out in front. 25x to the 2/3 equals 25. And then we use that reciprocal exponent, 3/2 on both sides. So when I'm doing 25 to the 3/2, again, we're doing square root of 25 to the 3rd power. Square root of 25 could be 5, or could be -5. So we have to consider both of those equations. I'm going to erase a little bit of this work because I need the space. So we'll have 25x on the left side. Everything else cancels out. 25x equals 5 to the 3rd is 125, or 25x negative 5 to the 3rd is negative 125. Then we just divide both sides by 25. X equals 5. If we divide by 25 over here, x equals -5. Sick. Last one. We have a cube root that we need to cancel out. The inverse of cube rooting is cubing. So we're going to cube both sides of this equation. Now, cubing cancels out a cube root. So like on the right side, it'll just be x plus 13. On the left side, it'll cancel out the root over the x, but the 3 was not in the root on the outside. So we just have to cube that normally. 3 to the 3rd power is 27. So it'll be 27x equals x plus 13. That's not too terrible. We could subtract an x, so we'd have 26x equals 13, and then we would just divide by the 26. 13 over 26 is 1/2. Sweet. Unbelievable. What else we got? Oh, function operations. So here are the 4 functions: x squared plus 4x minus 12, blah, 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 blah. Now we're going to perform operations with those functions, with those equations. So if you look at 13, it says a divided by b of x. So a's equation is the x squared plus 4x minus 12. We're dividing by b's equation, x squared minus x minus 42. I don't know. Luckily I can factor because I'm a pro. If I look at the numerator, it ends in minus, so I know that it has to be a plus and a minus. Factors of 12 that are 4 apart would be 6 and 2. To make them add up to positive 4, it'd have to be plus 6 minus 2. I look at the denominator, it ends in minus. I know that has to be a positive times a negative. I need factors of 42 that are 1 apart. That would be 6 and 7. To make them add up to -1, it'd have to be minus the 7 plus the 6. Now, do you notice anything? We can cancel out the x plus 6's, so you're left with x minus 2 over x minus 7. That's all you can do. Alright, c times d. So c's function is x minus 2 times d's function is x plus 6. So we just need to multiply these. We could FOIL that. X times x, x squared. X times 6, 6x. -2 times x, -2x. -2 times 6, -12. X squared, 6x minus 2x is 4x minus 12. Cute. Number 15, we're just adding together a and b. All right, so a is x squared plus 4x minus 12. When I add polynomials like this, I like to stack them vertically with some like terms. So when I do b, x squared, I put that under my other x squared. -x, I put under my other x's. And then -42, I put under my other constants. X squared plus x squared is not x to the 4th. You don't change exponents when you add. Look, we're doing 1x squared plus 1x squared. That's 2x squared. For the x's, we have 4x minus 1x. That's 3x. And then -12 12 minus 42 is negative 54. That is it, and we're having fun. Look at us, we are having fun. Oh, but on 16 we're going to do a minus b, a little bit trickier, not too much. So a we'll write first, x squared plus 4x minus 12. But when we're subtracting a polynomial, we're doing minus all this stuff. When I'm subtracting something like that, something I recommend is just make everything its opposite. So make it negative x squared, make it positive x, and make it positive 42. Because really what we're doing is minus negative x and minus negative 42. And when you minus a negative, you're really adding a positive. So here's our new problem. X squared plus negative x squared, gone. 4x plus x is 5x. Negative 12 plus 42 is 30. 5x plus 30. Fun! All right. Number 17, we're doing c divided by a. So c is x minus 2. A is that x to the fourth plus 4x minus 12. If you remember from earlier, we factored that to x plus 6 times x minus 2. Now, the x minus 2's are going to cancel out. You have x plus 6 in the denominator. If your numerator completely canceled, make sure you put a 1 as a place filler up there. And now we're going to do, goodness gracious, a times b. Oh, this one is going to be fun. So let's see, x squared plus 4x minus 12 times x squared minus x minus 42. This is going to be awful. Sorry. All right. When you FOIL, really all you're trying to do is make sure you multiply everything from one parentheses to everything in the other. So I'm going to get them all in x squared first. X squared times x squared is x to the fourth. X squared times negative x is negative x to the third. X squared times negative 42 is negative 42x squared. Done with the x squared. Now we're going to multiply them all by 4x. 4x times x squared is 4x to the third. I like to put them under my other x to the thirds. 4x times negative x is negative 4x squared. And 4x times negative 42 is negative 168x. I should double check that. 4 times 42. 160. All right, cool. Last one, we gotta get them all negative 12. Negative 12 times x squared is negative 12x squared. Negative 12 times negative x is positive 12x. And negative 12 times negative 42 is positive, I don't know, 12 times 42, 504. Look at that, we've got them already stacked and ready to go. X to the fourth. We have negative 1x to the third plus 4x to the third. That's 3x to the third. These are all negative, so we can just add them together and keep it negative. Let's see, 16 plus 42 is 58. Negative 58x squared. Negative 168 plus 12 is negative 156x. And we have plus 504. Brutal. Wow. Last thing, inverses. So inverse functions. Find the inverse of each one. So remember what we had to do here. We flip the x and y. And remember f of x is the same as y. So we're going to make this x. And we're going to make the x squared here, we're going to make it y squared. And you resolve for y. So if we're trying to get y by itself, first we would subtract the 11. Then you would divide everything by 4. X minus 11 over 4 equals y squared. And we don't want y squared, we want y, so you square root it. You can't square root x minus 11, that's okay. But you can square root the 4 in the denominator. Square root 4 is 2. And then at the end, you don't write equals y, you write equals f inverse x. That would be that one. One more. Switch the x and y. X equals equals cube root y minus 14 plus 1. And we're resolving for y. We're trying to get y by itself. I see a loose plus 1 back here. We could subtract that to the other side. Now I've got this group that's being cube rooted. The opposite of cube rooting is cubing. So we're going to cube both sides. Now the nice thing about this is you could just leave it as x minus 1 cubed. You don't actually need to cube that out. You could, but you don't need to. On the right side we just have y minus 14. All we got to do now is get rid of that minus 14 by adding it. So we have the x minus 1